We also are going to become aware of that there's several identities that we can discover and relationships between our six trigonometric functions. One subset of identities are called reciprocal identities, such that the sine of theta equals the reciprocal of the cosecant of theta, 1 over cosecant of theta. Cosine of theta, 1 over secant. Tangents, 1 over cotangent. And then likewise cosecants, 1 over sine. Secants 1 over cosine, and cotangents 1 over tangent. Those are called the reciprocal identities. We also have some quotient identities as well. Tangent also equals a sine over the cosine, and conversely, cotangent is cosine over sine. One of the benefits of this is that if we know the sine and cosine of any angle, then we can find the other remaining functions from that. So let's say that we are given a sine of theta is what? 2/5. And I'm given the cosine of theta is root 21 over 5. Nice number, isn't it? So given that, I believe that we can find everything else. So sine and cosine, check. Already done that. Sine or cosecant. So cosecant is 1 over the sine, which equals 1 over 2 divided by 5, which reduces down to 5/2. I could find the secant. Secant is 1 over cosine. Cosine is given as root 21 over a 5. Reduce that down as well, and that becomes a 5 over a root 21. And then to simplify that and rationalize the denominator, I'm going to multiply top and bottom by root 21 over root 21. And that's going to equal 5 root 21 over 21. All right, check. I've gotten 4 of the 6 so far. Tangent. Tangent, 1 over cotangent. Well, I guess I don't have a cotangent yet, so I can't use one of the reciprocal identities to discover that. I need to use one of the quotient identities. So the tangent is sine over cosine. So I'm going to have 2/5 divided by my cosine, which is root 21 over a 5. And that reduces down to 2 root 21. And then likewise, to rationalize the denominator for that one, let's multiply both the top and bottom by root 21. So my final is a root 2 root 21 over 21. And then the cotangent equals the other way, cosine over sine. Or now I can use maybe the inverse, the reciprocal function, since I know what tangent is. I can do it one of 2 ways. Let's try this way. So that's 1 over tangent equals 1 over tangent. I'm going to use this tangent right here that I got early on, which was a 2 root 21. And the reason why I'm going to use this value as opposed to this value in this one is just so I don't have to rationalize the denominator, because this reduces down to root 21 over a 2. Might be a good time to go back and remember how you work with complex fractions. Complex fraction is a fraction over a fraction. The better you're able to do that, or the better you're able to remember how to do that, will help in some of these types of ideas, and maybe you'll make some of the things I've just done not as confusing because you remembered how to do complex fractions. All right, the point of this is that there are several different types of identities with our trigonometric functions. We have reciprocal identities, and we also have quotient identities. That tells us that if we are ever given just a sine and a cosine, we're able to find the other 4 remaining trigonometric functions based off of those 2. We're also able to develop some more identities. These are called the Pythagorean identities. And how do we get these? We'll start with the Pythagorean Theorem. Says one side plus the other side squared. One side squared plus the other side squared equals the third side or hypotenuse squared from our basic right triangle. Now imagine I'm going to divide both sides by c squared. as I way to derive where I'm going with this. So I'll have some a divided by c squared plus b divided by c squared equals a 1. Now a divided by c, if I look at that from this angle, that's my sine. So I have sine squared plus cosine squared equals 1. So that's the basis of 3 more identities that we'll find useful, of which we call the Pythagorean identities. So let me list these for us. And as far as notation too, we're going to alter the notation just slightly on this. So I'll have sine squared of theta plus cosine squared of theta equals 1. That's one of our Pythagorean identities. With that, 1 plus the tangent tan squared of theta, that equals my secant squared of theta. And then lastly with that, should equal my cosecant squared theta. So I have 3 separate or 3 more identities for us to be aware of, and these are called our Pythagorean identities. And all those are derived from our basic Pythagorean theorem, and then from there I'm able to go ahead and derive one after another after another. So let's look at an example and use these as tools to help us solve something. So we can use that Pythagorean identity to solve this situation, where I know I have a sine of 3/5. Sine of theta is 3/5. Theta is acute, which means it's less than 90 degrees, greater than 0. So based off that, can I find the other angle in that triangle? Can I find cosine of theta? Well, which of these Pythagorean identities would be the most useful to me? I have sine, I want to find cosine. The first one has both of those terms, sines and cosines. Not aware of tangent and cotangents. So let's use this first identity right here. So sine of theta squared, so that's 3/5 squared plus cosine squared of theta equals a 1. Solve that for cosine. Same thing we've done before is isolate the variable terms. Variable terms in this one is cosine squared equals a 1 minus 3/5 squared. What is that, 9/25? One is also the same thing as 25 over 25 minus 9 over 25. Now they talk to each other. Equals 16/25. And then to get a cosine, not cosine squared, take the square root of both sides. So the square root of cosine squared is cosine. And the square root of 16/25 is 4/5. So what's cosine theta? Cosine theta is 4/5 if we're given the initial conditions where sine is 3/5. And that was by using one of our newly acquired identities, one of the Pythagorean identities.